Hello students, we will study this microcavity photodiode. This is asked a couple of times in the KT question paper. This is very important. Microcavity photodiode is a very fast photodiode. Actually, optical communication works in Gbps or terabits per second or more. So we should have a high speed detector as well. So microcavity photodiode comes under the category of high speed photodiode. So I will explain the work. Okay. So this is a general block diagram of a photodiode. You are aware of this one. So this is a depletion region where the incident photons are coming, and they separate out the electrons and holes. So there is an electron flow from the through the junction of the diode. I mean through the diode, and so that makes a photocurrent. And this is a photodiode. All photodiodes are reverse biased, right? These things we studied earlier, and so that explanation is here. PN junction and the photodiode is a PN junction diode, and reverse bias. Reverse bias is used for working of photodiode. So the application of light in the junction, the depletion region. So there will be photocurrent depends upon the absorption of light. Okay. So photocurrent generated proportional to the absorption of light intensity. So this is a characteristics of a photodiode, and you can see that when light intensity increases, photocurrent also increases. For 2 milliwatt light power, so approximately 1 milliampere current, and for 10 milliwatt light intensity, you can see 4 milliampere. So light intensity increases, I mean photocurrent increases with the light intensity falling on the depletion region, right? IPO area, okay. So, so what is optical cavity or Fabry-Perot cavity or optical cavity photodiode? Okay, microcavity photodiode. So different names are here. You can see this one. So what we are doing is a Fabry-Perot cavity. So a Fabry-Perot cavity actually is containing two mirrors, mirror 1 and mirror 2, separated by a finite distance. It can be capital L. I am using capital L. The difference separation between these two one, and mirror 1 is 100% reflectivity. So all the, if any rays comes here, it is completely reflected, and mirror 2 is less than 100% reflectivity, that is in the order of 95% to 98%. So reflectivity is a power. So R1 is the reflectivity of mirror 1, R2 is the reflectivity of mirror 2. And you know that if some rays are incident this here, because of higher reflectivity of these mirrors, there will be multiple reflections. So one ray coming here and reflected back, and coming here, reflected back. Similarly, all rays are falling on this cavity, multiple reflection will be taking place, right? So there is these rays are coming out, constructive interference and destructive interference. So you studied these things from your +2 classes. So the constructive interference condition is equal to 2L is equal to N lambda. L is the separation between these two mirrors. So why 2L? So one rays coming here, going here, and coming well. Full round trip time, that is 2L. 2L is equal to N lambda. Lambda is the incident photon wavelength, lambda, okay? N is in integer, it can take value 1, 2, 3, etc. So those modes means those rays satisfy this condition. 2L is equal to N lambda coming as this type of wave. These are called modes. Modes you studied in optical communication, micro technology, antenna and wave propagation. Everywhere you studied. So those modes satisfy this condition coming out as constructive interference and coming out here. Then how can we use this one in photodiode? So photodiode, the condition is that, so high data rate optical communication, high speed photodiode as a detector, right? So high quantum efficiency. What is quantum efficiency? Quantum efficiency is 100, means all the incident photon creates that number of, suppose 1000 photons are coming, 1000 electrons are generated, then quantum efficiency will be 100%, right? So for that, we need a thick absorption layer. I mean, suppose you remove this complete rectangular, instead of this rays here and these two lines, orange line, just take the rectangle alone. That is a depletion region. If the depletion region width is increases, what happens? So more incident photons are coming, more electron hole pairs are generated, right? So what is the disadvantage there? The disadvantage is that the electron has to travel more distance. So transit time is more, the speed of operation will be less. But quantum efficiency is higher, but the transit time is more, so the speed is less. If you reduce the size, the rectangular 25% of this original size, what will happen? then only less number of photons are incident on this depletion region, right? So less number of photons means less number of carriers are generated, photocurrent will be minimum. So there should be a compromise between these two. So in order to compromise, in order to get rid of this problem, what we are doing is we will put this Fabry period cavity in between in the depletion region. What will happen then? So when some racer manages to reach here in the depletion region where immobile carriers are there, so these rays are going multiple reflection. I am showing only 3 rays are here. They are coming here, coming back, again coming, going there, and so multiple reflections are there. So because of multiple reflections, so more number of carriers are generated because these rays are absorbed by the this immobile carriers and making electron hole pairs, right? So less number of rays because of multiple reflection in the cavity and more carriers will be generated. I repeat, less number of rays, the depletion width is very minimum, but less number of rays are falling on the depletion region. But because of multiple reflection, more, and then we can see that more rays are there. Okay. Because of multiple reflection, more rays are there. So more rays this interact with the immobile carriers and generate more electron hole pairs and more current will be generated. So both our application, that is, it increases both quantum efficiency and bandwidth. So that is explained here. PM gallium arsenide is the cavity here, Fabry period cavity here. The absorption and quantum efficiency therefore enhanced because of Fabry period cavity. You can see the helium gallium arsenide and the mirrors are formed by this P region and N region. Okay. So these are the advantages of microcavity photodiode. High quantum efficiency. Quantum efficiency means all the rays are trapped. It is trapped inside the this Fabry period cavity. So multiple reflections because of this multiple reflection, more carriers are generated, more corresponding more photocurrent, and detection speed because small area is used and the Fabry period cavity inside there. So small area, small number of rays because of multiple reflection, so more carriers will be generated. So quantum efficiencies will be high and speed of the operation bandwidth will be high. And main disadvantage is manufacturing complexity. Complexity increases, the cost also increases. So that's all for the time being. Thank you very much. Thanks for your kind listening.